Audio check. Let's do both.
Let's get started.
It moved forward. It wasn't. There we go. Okay. Good morning, everyone. Welcome back to the second day of the NHFP Symposium. We used to many of you know Paul Green, who was the Einstein lead. Yeah. And he's retired now. Last seen at a cafe in Vienna, I believe. But he was a strong proponent of the open mic and threatened to sing at it. And finally he did. And if you didn't sign up, I'm not going to do that because I won't. I'm not that cruel. But I will tell you that at this open mic session, I plan to teach you how to tie your shoes. Most of you, probably 90% of you, have been doing it the wrong way all your life. There is a simple way with a slight change, but one slight change to the way you do it, where a single knot is far more effective than that crazy double knot they teach you where you use this loops again, right? It just far more effective, unless you tend to step on your laces a lot. So I'll show you that, and it works really well. And some friends I've shown it to have said, it's changed. I've never tied my shoes again. And I said to her, so you don't take them off? And she said, no, I just don't retie them. So, okay, you'll have to tie them every morning, but outside of that, they stay tied. All right. So, I mean, what more could you ask for? So, the open mic, sign up. Hopefully you've got something more interesting than tying shoes, like, your baking, your singing, your piano playing, your poetry, your art, whatever you like to show. And, we gave the committee a couple of more than that. We give them a lot of money to go buy refreshments. And so, if there's no open mic, there's no refreshments. So come. All right, and we'll put this URL in the main Slack channel, fellow Slack channel. All right. Okay. Now let's do some science. Sorry about that. Okay. Let's go back to yours. I think was just up there. There we go. I want to do this. There you go. Okay.
Awesome. Thank you, Andy. Again, welcome to day 2. Excited to be here. Hope you all are too. And Massimo is going to kick us off today with something that sounds super interesting. Let's hear about those H0 constraints from lens supernovae.
Okay, great. Thank you so much. So I'm Massimo Pascali. I'm starting this fall as an Einstein Fellow at UCLA. Today, I want to talk to you about the first measurement of the Hubble constant from a strongly lensed supernova 1A. Afterwards, Justin's going to tell you about the second one, so this is a little less ceremonious. But why is it that we want to measure the Hubble constant? Hopefully, everybody is aware, but of course, knowing H0, it's a crucial parameter for our cosmology, right? If we want to know the age of the universe, we want to understand dark energy, curvature, we want to know what H0 is. In the last 10 years, it's emerged as this sort of hot topic, which is Hubble tension, right? There's this tension between measurements that we make from things like local distance ladder at late times and measurements that we make from data in the early universe, like the Planck CMB data, that assumes a cosmological model, right, to measure H0. And so it assumes this lambda CDM model. And so this tension seems like it could be a potential threat to the lambda CDM model, right? That there's this 5 sigma difference between the late and early time measurements. And so could it be that our cosmological model that is otherwise very robust, is very successful at a wide range of cosmological observations, could have some issue? And And while I think that's very exciting, before we jump to any new conclusions, right, things like new physics and such, I think we should do some checks, right, to make sure that we've overcome all of our systematics. Well, so you can see, like 20 years ago, most of the measurements seemed to agree. And then as we got new observatories, methods improved, of course, the precision on these measurements went down and created the Hubble tension. And it's, of course, important to keep pushing these methods, to keep improving them and get higher and higher precision. But I think that we want to introduce some new methods into the mix, right, to hopefully overcome any systematics that seem to be unknown with any existing methods. And so one approach for doing this is to use the time delay between different lensed images in strong gravitational lensing. This was postulated all the way back in 1964 by Sir Ralph Stahl. The idea is that you have some lensing galaxy here you see in the foreground. In the background, there's some source that gets lensed by this galaxy such that it appears at 4 different angular positions on the sky. And so the photons that travel from the source to those lensed images that we see, there's a time delay in the arrival of those photons due to the difference in the geometric path length that the photons actually have to travel, as well as the Shapiro delay that's induced by the lens potential. And so what Ralph Stahl figured out was that, it gets a little cut off here, but that this relative time delay between the images is equal to 1, this phi lens. This is what we call the lens potential. You can sort of think about it similarly to a Newtonian potential for the lensing galaxy. And so you can get this phi lens from something that we call strong lens modeling. This is typically known to some decent precision just based off the lensing evidence. And that also some angular diameter distance, this d delta t. And of course, the angular diameter distance, it's dependent on cosmology, right? And so if you somehow have this phi lens, which I mentioned we can usually get, and you somehow measured what this delta t was, this delay between the different images, you could actually use this angular diameter distance to back out the Hubble constant, right? That's what Ralph Stahl had originally predicted. And of course, this is a one-step measurement, right? You don't have to build up a distance ladder. It's a single rung measurement, so that's very exciting. The main issue is that you need to be able to measure this delta t, which you typically don't get to do, right? Because these images are static. There's no way to measure the delay between the different images. You need something transient to go off. And what Ralph Stahl had predicted was that if a supernova went off in this lensing galaxy, then you could actually see the 4 different supernova images, map out the supernova phase, get the delta t. We, of course, know phi, as I mentioned, and you can back out what the Hubble constant was. And so this, as Ralph Stahl had predicted in the 60s, would not actually be realized until 50 years later in 2015, where they discovered this Einstein cross configuration. So here you can see the template image. This is the lensing galaxy. There is a galaxy that's quadruply imaged about this. And then when the supernova goes off, you can see the 4 different point sources. So a huge realization of Ralph Stahl's original prediction. And of course, they named it after him, supernova Ralph Stahl, right? And so this supernova, as you see it here, unfortunately not very useful for cosmology. The reason being is that it's sort of what we call a galaxy-galaxy lens. It's one galaxy lensing another galaxy. And the time delay that it induces between the images actually isn't very big on this scale, right? So it ends up being that the time delay is like a couple of days. And you have to do cadence photometry to actually map out the light curve. And so that uncertainty is about a couple of days. That uncertainty directly propagates to the Hubble constant. You end up with an H0 that's not very useful. What's so great, though, about this is that it's not only a galaxy-galaxy scale lens, but it's actually also a cluster scale lens. So what you were seeing was down here, and then here's an entire galaxy cluster that's inducing 2 other images of the galaxy, this time with a much greater potential, hence a much longer time delay. And so what you can do is, because we know this phi lens, this from strong lens modeling, they're able to back out the phi lens, and you make an assumption reasonably about what H0 is, you can actually predict what the delta t is between these different images. And what people predicted was that there would be another image that appears here in 1.2 about a year later from 2015. And indeed, HST confirmed and found this supernova in early 2016 imaging. They found this SX. This time with a year-long time delay and an uncertainty of about a couple of days, right? So this is actually quite useful for measuring the Hubble constant. So we have one piece, all right, which is to get that delta t. The other piece was this phi lens that we get from modeling the lens using the lensing evidence. And so usually this phi lens, there's different approaches to doing it. The reason being is that you have to parameterize your lens with dark matter. We don't know what dark matter is, right? And so there's different approaches. Usually they agree pretty well, and so we don't have to worry about differences between them. But if we're doing cosmology, right, then we really need to make sure that there are no systematics in our phi lens. And so what they did was that they used this delta t, but they used 7 different approaches for modeling the lens. You have 7 different phi lenses, each one contributing to this measurement of the Hubble constant from the delta t, but using lensing evidence to sort of weigh them to make sure you get an accurate value, right? And so they actually got a sub 10% precision, like a 6% level precision on the Hubble constant with a single event, right? This is quite exciting. Of course, the precision itself is not enough to actually confront the Hubble tension, but you can imagine that if you had a couple of these events, right, a handful to a dozen of these events, suddenly you're starting to get really competitive, right? And so unfortunately, these lens supernovae, they're quite rare. And so, in the meantime, while people were waiting for more, they were thinking, okay, well, how can we take this supernova ref stall to its absolute limit and get a better precision measurement? And so what they realized was that the precision was limited by the lens models, not by the actual time delay measurement. And so they said, okay, well, what if we incorporate more lensing evidence? We try to make these lens models better. But unfortunately, they really ran up against this 6% precision level. They couldn't improve anything. But what the lens modelers found was that if they had a measurement of the magnification of the supernova, which was degenerate with the Hubble constant, they would actually be able to get a better measurement of it. Unfortunately, this was a core collapse supernova. They're never going to get the magnification. You rarely get the magnification in strong lensing to actually be able to measure it. That is until 2023 in JWST NIRCam imaging as part of the PEARLS program comparing to existing HST imaging, we found a triply image supernova. So here's a triply image galaxy, and you can barely make out, but there is a point source there that appeared here. And so we saw this triply image supernova. Lensing models of the phi had predicted that the time delay was relatively long because it's on this galaxy cluster scale, so viable for cosmology. And we submitted a DDT to do multi-epoch photometry to map out the supernova light curve, as well as spectroscopy. Spectroscopy confirming that this supernova is a type 1a. Here you can see the smoking gun signature of the silicon-2 absorption. A type 1a being a standard candle, meaning that we're actually able to get the magnification of this object, this thing that people had lamented not being able to do for f stall, we're actually able to do here. And so using the multi-epoch photometry, you're able to map out the light curve. And so this is work that Justin did, who's giving the next talk, to map out the light curve photometrically. Using the spectroscopy simultaneously of all 3 images, the spectroscopic evolution of 1As is well known, and so you're actually able to back out the time delay spectroscopically. This was totally novel. This hadn't been done for something like ref stall. And then using these models that had been made from the fitting, you can actually back out what the magnification is by comparing to the existing sample of type 1a supernovae. So this totally new observation that people weren't able to get in supernova ref stall. And so what we did was we commissioned 7 different independent teams to construct lens models to get this phi lens using different approaches. And we compared that to these measurements of both the time delay and the magnification from both photometry and spectroscopy. So each of these points is the different lens models, and the swaths are sort of the predictions from photometry and spectroscopy. This delta t directly allowing you to measure the Hubble constant, and this mu, this magnification, allowing us to weigh the different lens models and weed out models that seem to be somewhat inaccurate, allowing us to get a more accurate and more precise measurement of the Hubble constant, right? And so what did we end up finding for this inference? Here I have 3 different inferences of H0, and I've ordered them by having increasing constraints that we place on the inference. So what I really want you to focus on here is all of these different colored curves that you're seeing. So each curve is the contribution of a different lens model to the overall inference. And so you can see up top, this is sort of the least amount of constraints. This is using only the time delay. You could think of this as like almost like type 2-like. It's like what they did for f stall. And you can see all 7 of these lens models, they're kind of coming out to play, right? Each of them are making different predictions, but they're all sort of contributing to this inference. And so it adds to this spread, right? And what we want to do is we want to weigh each of these contributions based off their accuracy or their ability to reproduce the constraints. So as we increase the constraints, you can see certain lens models get punished, and we have a fewer remaining amount of lens models. As we incorporate all of the constraints, that being including this magnification that was unavailable for f stall, as well as these spectroscopic constraints, also unavailable for f stall, that one lens model, one color curve, ends up dominating the total inference, right, with some subdominant contributions by the other lens models. And so indeed, when we incorporate this magnification constraint, we're able to get to more precise, more accurate measurement of H0 here, and we actually get something very impressively at the 8% level, which is greater than what was done for Refstall. So you might be thinking, okay, well, but we had more constraints here, but the time delay constraint wasn't quite as good for Refstall, right? So actually the magnification ended up being quite powerful here. And it's going to end up continuing to be very powerful because the supernova has more to offer. We can actually get even better constraint of the Hubble constant. The reason being is that all existing JBIS-T imaging had the supernova in it. And getting good photometry of the supernova is difficult when you have the host galaxy right there. So in 2025, we got follow-up imaging to act as a template to do difference image photometry right after the supernova had faded. So here you can see supernova hope is gone. We could subtract these two images and get effectively pretty perfect photometry. And that's going to improve the time delays and the magnification. Actually, I'm hopeful that that combined with new lensing evidence is going to get the Hubble constant down to about 5% in this single system measurement, which I think is very exciting. And when we look forward, there are other supernovae that have already been detected or will go on to be detected from large programs like the JBIS-T Venus program, which is looking at many clusters, things like the Rubin and Roman observatories that are expected to yield dozens of these supernovae. And if we're continuing to get things that are at the sub 10% precision, we're going to pretty quickly get to something that's very effective for measuring the Hubble constant and is competitive with other premier measurements. So I'm very hopeful for this field going forward in the next 5 to 10 years. Thank you.
Massimo, super cool stuff. I have a ton of questions. Who wants to get in before me? Abby.
So when you derive the magnification of the supernova, was that dependent on the magnitude? So would it be dependent on the local clutter anyway?
Right, so we use the existing, so we back out the model from the existing spectroscopy and photometry to get what the predicted observed B-band magnitude would be, and then we compare that to the existing Pantheon Plus model, which gives you B-band versus redshift, and we interpolate between, so it ends up being model dependent. It's interpolation dependent, and that's accounted for in the systematics.
At the back?
Is there a way to understand, you have 7 different models and only one of them ends up fitting? Is there a way to understand where this kind of process converges in terms of the complexity of the lens model? Because, for example, for much simpler systems, there's issue of the mass speed degeneracy, right? For not, and here you have much more complex systems with many more observables, but your corresponding system is also a lot more complex, right? So how do I know when to stop in terms of the
Right, yeah. So I think there's actually 2 questions hidden in there, so I'll answer both of them. So I agree, these are complex systems because we're dealing with a cluster scale lens, right? It's not these galaxy lenses. You get both a benefit and a punishment for the complexity, right? One, of course, is that it's complex. You need more parameters, you need a more complicated model. The benefit is that you actually get to overcome this mass sheet degeneracy, which usually plagues these galaxy scale lenses, because you get many different sets of lensed images at different redshifts, so it breaks at a certain degeneracy. But it's a good point, how complicated do we make these models? Generally, you want to make them as simple as you can while still producing the observables. You can use typical ways to grade the complexity of the model, things like your reduced chi-squared, your Bayesian information criterion and such. And so all of these are ways to do it. I'd say that is still an active area where we are trying to improve and to determine how complex the models are. But I don't think it's a huge problem right now. I think the models are sort of sufficiently simple.
All right, we'll have our last question here at the front while Justin comes and gets set up.
Hi, Maxwell. Very nice talk. I enjoyed it. So, I mean, as we've talked about, the central issue seems to be the accuracy of models. And, I mean, as you see from the data, many models just are not very good. They don't reproduce the observables. So I guess my question is, how do we know if any of the models are good? And what I mean to say is you don't have so many observables. Your observables are sufficient to rule out some models. So it's necessary, but it isn't sufficient to show that at least some model is right. I mean, a silly example, you could ask 8 people to guess flipping a coin, and none of them know how to do it, but they all think they do. And, one flip, half of them are gone. Another flip, half of them are gone. Another flip, now one is left, and you just don't have more flips to know none of them are actually. So my question is, how do you know any of the models are accurate enough for predicting the Hubble constant?
Right. So I think that this isn't going to be one of the greatest challenges that we face going forward in this part of the field. First of all, I'd say that these models are more accurate than flipping a coin, right? We have strong priors and we understand dark matter to be on these lensing models. We've taken these different models and they've successfully produced a number of observations across a number of different clusters across the sky, right? So I think we can believe that our models are sufficiently accurate, generally for describing these cluster scale potentials. But if we want to better understand lens model systematics and we want to actually fold that in and see what directions to push our lens models, because they weren't necessarily this level of precision, I think that's what makes these lens so important. That's what makes these type 1A supernovae, we actually get the magnification so important, that now we have this sample of different lens models constructed using a variety of methods, and we're actually able to test them and determine what the direction forward is to improve the accuracy. So I think that you've really hit on an active area that needs to be focused on, but I'm confident that given the current data set to the emerging data set, that this will be solved.
All right, let's thank Massimo again. And next up, we have Justin, who's going to tell us about siblings.
Is this one on? Good? Yeah, okay, cool. Great, yeah, I'm Justin Perel. This is my third and final symposium, and I'm here at Space Telescope, so finishing it at home. I'm going to compliment Massimo by talking about another multiple image supernova, strongly lensed supernova Hubble constant measurement. And I'm hoping that you either, one, still care about the Hubble tension, two, care about supernovae and this is still cool, or three, I hope you just say, this is really cool, because this one actually is a very interesting system, and I think you'll be wowed. That's my hope. So Massimo talked more about the lens modeling side. I'm going to talk more about the supernova side. So in this scenario that he was describing, light is being bent around some intermediate object. In this case, a galaxy. In our cases, a cluster of galaxies. But in either case, you end up with this kind of multiple image system. And the difference in these path lengths, or the paths through the gravitational potential, is what causes this time delay that is the 1/2 of the problem for getting the Hubble constant. This is kind of a graphical representation of that happening, as this one is sort of coming from the geometry, but as Massimo said as well, most of the difference actually comes from that path through the gravitational potential. And you can see here at the bottom, you can imagine if you had a stopwatch, you could say, okay, whoa, this one arrived here, this one arrived here, and this difference is exactly the time delay that you're looking for. So if you were able to measure just this sort of delta function arrival, this is what you'd be trying to get. In the case for a supernova, it doesn't quite look like this. Instead, it looks something like you observe, you see a light curve for your image A in this case. You keep watching and you see another light curve for image C. It's the same supernova, but you'll see some difference in arrival. That's the time delay on the x-axis here. This thing is hard to use. Okay, well, yeah, that'll work. Okay, we'll move to this one. And then the magnification is going to be slightly different from this as well, so you might see them at different brightnesses, but otherwise it's the same intrinsic supernova. Yeah, okay. So in the case of this, the one that I'm going to talk about, this is the lensing system. It's a cluster, just like we just saw. This thing is quintuply imaged. The host galaxy is this 1, 2, 3, 4, and 5. And back in 2016, there was a supernova here called supernova Requiem. It was observed in HST imaging archivally, so it was not detected until 2019. But this image is from 2016. You can see 3 images of the supernova here. And you can sort of tell by eye that this is not just some compact object in the galaxy, because it's a different color. It's the same thing, but it's 3 different colors, and that comes from the supernova evolution. In 2023, we took a new image here, and you can't see it, this zoomed out thing, but very close to the core, there's actually another triply imaged, well, it's quintuply imaged, but 3 visible images, A, B, and C, of another supernova, which we named supernova Encore. This was the first time that we'd seen multiple lens supernovae coming from the same host galaxy. This is at redshift 2, so making it also the first sibling galaxy redshift greater than 2. And this gave a really interesting opportunity. One, because you can measure the Hubble constant from 2 different supernovae in the same system, kind of double the constraints. That's never really been tried before, been possible before. And 2, supernova Encore is once again a type 1a supernova. So another opportunity, as Massimo was just saying, to use it to constrain not just the time delay, but also the magnification using its intrinsic luminosity. Problem again is that we don't have a template, the same as what Massimo was just saying. Because we observed this originally with HST, then we came back with JWST, and there's obviously all the filter mismatches. We don't have a template for all of our JWST imaging. We built a model instead. So we did scene modeling to try and disentangle what is host galaxy, what is supernova. But there's a pretty large systematic in that because we don't know what's actually underneath the supernova itself. And so this ends up being our dominant uncertainty once again. But as Massimo also said for Hope, we are coming back in December to get a template of this. And so you'll see at the end how that affects our uncertainties. But doing that process, you end up with photometry that looks like this, where the lower light curve is coming from one of the images of the supernova, and the upper light curve is coming from the other image of the supernova. So you can kind of tell just by eye, maybe looking at this one in particular, that these are coming at 2 different phases of the supernova evolution. This one's a bit steeper than this one. So just by eye, that's kind of the constraint that we're going to get. So when you actually try and measure the time delay, what you end up really doing in this case, because we don't have that scenario where we get a nice full light curve twice, like I showed in the cartoon, we ended up catching this after peak brightness. So we're basically on a straight line, which makes it quite difficult. But what we end up doing is basically saying, okay, well, this comes from the same supernova. It's 2 images of the same supernova. So where do they fit on a single model? And so you can see here that like the first 3 points come from one image of the supernova, the next 3 come from the other image of the supernova, and they create one single intrinsic model. So we basically get, sort of as though we had just observed a single supernova at redshift 2 for this entire light curve. This fit quite well, with all the uncertainties in photometry and whatnot. And this is where we ended up on the Hubble constant list here. So at the top is the lens supernovae, Refstal, Hope, and this is Encore. The uncertainty is, as we said, relatively large due to the uncertainties in the photometry. But with the upcoming template, both for Hope and Encore, our projections are that this will turn into something like this. So this is based on the initial work we've done with the template we have for supernova Hope, as well as sort of the corresponding projections for Encore, where the lensing system is actually a bit simpler. So the lens model uncertainties are slightly smaller. But this still will not by themselves obviously determine the difference between the Hubble tension. But with 3 here, we'll see where these land. The change in this uncertainty doesn't take into account that these could obviously shift as well anywhere within those uncertainties. So it's very possible you could end up with these all lining up over here, or we could end up all the way up here, and then things will start to be a little bit more interesting. So that said, great. We'll end up here in a few months. That sounds very cool. But what about the other supernova? So supernova Requiem, 2016, these 3 images. But what about up here? This image is expected to reappear pretty soon, actually. Back then, in 2016, we looked at this, and the initial lens model said 2035 or so. With the new constraints that we've got in the meantime, this is what this prediction actually looks like. So basically, you can look at dates on the top and Hubble constant on the y-axis. So basically, the prediction is that supernova Requiem will reappear sometime between this coming May and next January. The particularly interesting thing here is that this time delay is so long that the uncertainty in the lens model is not the dominant thing anymore. The dominant uncertainty is the Hubble tension itself. So if H0 is down here in the 67 range, then we really don't expect to see this until next year sometime. But if the Hubble constant is higher in the mid-70, 73, then we would expect to see it soon, this spring or summer. So even before we do things like follow the supernova, measure the time delays, get a new measurement on the Hubble constant, just the rough date that it arrives will be a pretty strong constraint on the Hubble constant. So this is pretty cool. We have a program to monitor the cluster starting this year, going all the way until next year with HST, and then once we detect that there's a supernova there, triggering J2ST follow-up to get a very nice detailed picture of what this supernova looks like. So reappearing in 2027. Then also reappearing in 2033-ish. So this system will end up with a Hubble constant measurement from just these, then from these compared to this, from these compared to this. So there's this whole system with just not that many observations really will give us essentially 3 different Hubble constant measurements. So that's quite cool. Unique so far. But the last 2 months have been quite extraordinary as well for lens supernova discovery with J2ST. So those 2 that we just showed, Encore and Hope, were basically the first 2 years or so of J2ST observations, 1 per year. This year we've had observations from a new galaxy cluster program called Venus. It's observing around 60 clusters with J2ST, which is really just kind of an order of magnitude more than we've had in the past. And already in the last 2 months, we've had a few discoveries. So first, this is called supernova Aries. So we had a discovery here with another reappearance predicted in like 50 years. So we're hoping that they wheel me out on the stage for that one. I knew that was coming. So that's very cool. We already have the data for this. It's a type 2 supernova, and we got a really nice spectrum of that. This one as well, complicated, but just zoomed in over here. This is a quintuplet image, so these are zoomed in on each of the 5 images. And this one here is at redshift 5.1 and magnified by a factor of 30 in each of these 2 images. And so the time delay is very small, hours, so we're not doing cosmology with this, but we get a ridiculously high signal noise spectrum of redshift 5 supernova in about 12 hours. So we'll check that back sometime later this week. And then just while I was sitting in the audience yesterday, one more, this is a triply imaged galaxy at redshift 0.9. And this is actually the template image because that's what I had a color image of. But right about here, there's a supernova that is just appeared yesterday in new imaging from Venus. And it is the second to arrive. So this one came some years ago, 10 years ago or something. This one we're catching live, and we predict a new appearance of the supernova around here in about 2 years. So another really rare opportunity, well, not becoming so rare, but rare until now, to predict another reappearance and actually detect it on like kind of a usable timescale of a couple of years, giving us a Hubble constant measurement, on the order of that same 5 to 6%. So Venus really revolutionizing this. Overall, lens supernovae, I think, are extremely cool. I hope everyone thinks so as well, even if you don't care about cosmology. Being able to predict and find the reappearance of a supernova, done once with supernova Refstall, and now about to be done a couple more times, both from Encore and this new supernova, which we named Athena. The combined constraint on the Hubble constant that we expect from Requiem and Encore is on the order of 3%. And just in the next few months, we'll have new measurements from both Hope and Encore that will cut the current uncertainties roughly in half. Thanks.
Thanks so much, Justin. This is sick. Who wants to kick us off? Abby, again.
This is super cool. What do you kind of think is the dominant systematic uncertainty in this right now?
Yeah, so there's kind of answers to that. So in general, the answer is going to be the lens modeling side. At the moment, it's the supernova side because we only have like 3 epochs per supernova. So for the Encore and Hope measurements, the dominant side is actually the supernova side. Once we get the templates, they'll be roughly equal. But in general, we expect the dominant systematic to be from the lens modeling side. And so we will struggle to get below this sort of 3% range because of that.
Yep, at the front. Go ahead.
It's been very nice talk, Justin, and very cool stuff. So you're going to be in the regime where you start to combine multiple lens systems. And if model uncertainty is your biggest uncertainty, and these are some of the same models from the same people, how do you deal with model covariance?
Yeah, this is something that I think almost need like a whole conference on. Is lens supernovae are just starting. We've been able to sort of say like one at a time. Now we'll have 3, and soon we'll have 5. So then this starts to be a much.
I mean, do they go down as root n? Probably not.
Probably not. So in our proposals, yes. In reality, not, especially because we purposefully use very different lens models in order to make sure we're sort of like not tricked by a single method. But that both introduces very complicated covariances, and also a lot of them are weighted to basically nothing, and so then you end up with just using roughly the same one or two models every time. So these are, I don't have an answer for this, but I do think.
How do you even do it? Like, how do you even figure it out?
At the moment, I would just like average and keep the weights that we are using, and then we'll have to do some sort of crazy. I'm worried about the fact that we don't. First of all, I'm just generally worried about this, but I'm worried about the fact that we don't have sort of like consistent weighting methods yet across each time. So we've used 3 different weighting methods to be clear for the 3 lens supernova measurements, and that's partially because we have different types of supernovae, partially because we have different observables. So I don't really know. I mean, we don't have a consistent way to do it yet.
I mean, it's really the covariance. I think,
yeah.
Just the issue.
Yeah. I think we need a actual probably what is the future of not just individual measurements anymore, but we have Rubin coming, we have Roman coming. We should end up with dozens of these. We will want to combine them, make sure we have it correct, before just sending out numbers. But this year, it's time to do it. I think when we have 3 to 5, we'll probably try it. So.
Maybe a final quick question for Justin while we do the changeover to Andre. Yep.
So I don't know if X-rays come into this play because with Chandra you could, in theory, detect 4 images of this if there is an X-ray.
Yeah, we haven't tried. We've restricted full UV to. We are going the other to mid-infrared for this redshift 5 stuff, but we haven't really talked about X-ray.
The cluster X-ray foreground is bright as well. So
yeah, in the clusters, yeah, I was just.
But if it's very X-ray, I mean, it depends on the type, I guess.
Yeah, I don't do supernova, so I don't know. I know that supernova remnant appears at some point. It would be complicated.
Yeah, not sure how much it would add, but it'd be interesting.
Then have seconds separations, and then you don't see the galaxy.
No.
All right, let's all thank Justin again. And next up we have Andre, who's going to tell us a little bit more about DESI. Go ahead.
Thank you very much. It's a great pleasure to be again at the Hubble Fellowship Symposium. This is also my last symposium, so thank you for having me. It's been an extreme pleasure to go through all of this. So today I'll tell you a little bit more about DESI, and my talk will actually have 2 parts. There we go. So my talk will actually have 2 parts. In the first part, I'll give you a few more details about our baryon acoustic oscillation analysis using DESI DR2. So this is a continuation of Christian's talk from yesterday, where I'll be going into the measurements. So our DESI DR data release 2 sample covered the first 3 years of DESI observations. This was about 14 million galaxies and quasars, and it delivered a significant improvement over our DR1 results, so about a 2.4% improvement. Now, I know Christian already introduced baryon acoustic oscillations yesterday, but I have this video that I really like showing, especially for people who are not cosmologists, because I find it really gives you an intuitive idea of the core of our measurement. So these baryon acoustic oscillations form in the early universe before recombination, and they're oscillations in the primordial baryon photon plasma. And then after recombination, they get frozen in the matter distribution. And then that matter distribution is free to evolve under gravity and collapse and form the galaxies that we observe in the universe today. So you can think of this matter distribution being sampled by these galaxies. And of course, this is a very exaggerated view of our universe. We don't actually see these circles in the universe. But then when we go and do our survey, we're essentially just building a very large three-dimensional map of our universe. And then the core of our measurement is just a simple histogram. So we just go through every single galaxy pair in our map. And then we count up the distances, and we build this histogram as a function of the separation between galaxies. And if you do this with enough galaxies over a large enough volume, you start to see this very beautiful picture form, where there's a characteristic overdensity at about 100 megaparsecs divided by h, and this is exactly that baryon acoustic oscillation feature that was left imprinted from the early universe. So the power of DESI really comes from the fact that we can measure this in 3 dimensions. So we're not just measuring this feature across the sky. We also have line of sight information, and that comes from the fact that we can measure very, very precise redshifts. And that means that our BO results are actually 2-dimensional. So we're measuring this both across and along the line of sight. And you can see here the relationship to the distances. So we have this angular diameter distance, the m. This is from the measurement across the line of sight. And this is an integrated quantity between us and the redshift, the effective redshift of our measurement. And then we have this dh, which is just the speed of light divided by the Hubble constant. And this Hubble, sorry, not Hubble constant, a Hubble parameter at the redshift of our measurement. And this is really why this line of sight measurement is very powerful. It's because it gives you a direct insight into the evolution of the universe at the redshift of your measurement. You can also reparameterize this, and if you look at our papers, a lot of measurements are given into these 2 parameters at the bottom. They're capturing exactly the same information. So instead of looking at along and across the line of sight, you're just looking at isotropic BO scale and then the anisotropy, or also known as the Alko-Paczynski effect. So a key step in our analysis is that we're doing all of this blinded. So for the vast majority of our analysis process, we don't actually know the result. We can see that correlation function, but the data points are all systematically shifted in a way that blinds us to the actual underlying cosmology. And that allows us to make the huge amount of choices that we have to make through our analysis without being influenced by what's the final outcome. And that analysis process is very complex, and there's a lot of people involved, and we have a lot of supporting papers. So if you're citing any of our work, please also cite supporting papers. There's a lot of early career scientists that spend many years working on this validation papers, which are the underlying thing that make all of our analysis and main measurements possible. So here I'm just talking about the Lyman alpha forest BO measurement. You can see the plot on the right shows a large list of analysis variations, and the idea here is that at this stage we're still blinded. We're just going to every single choice in our analysis, and we're doing different variations around those choices to see whether we have any potential problems and whether our results are robust. And then the same sort of test for the galaxy BO measurement, where now you can see the different plots are different redshift bins going all the way from lower redshifts to the quasars at high redshifts. And again, supporting paper there at the bottom, please cite them if you're working with our results. And then finally, once we're happy that we're passing all of these tests, we take a list of all of the systematics that we think are important and we've detected with a high enough significance, and then we fold this into our final results. And for the DR2 analysis, we had the unblinding in December last year. So for the Lyman alpha part, we did it on Zoom, and you can see all of us very happy there after just after seeing the results on Zoom at the top. And then for the galaxy clustering part, we did it at our collaboration meeting a week later, and you can see all of us there. We had a very intense unblinding session at about 8 p.m. in the evening, and everyone was in the room, and nobody wanted to leave for dinner just because everyone wanted to see the results. So Christian already told you about the cosmology, so I'll just leave you with these beautiful measurements, where here you can see the improvement between our DR1 and DR2 results from the empty circles to the full circles. And overall, most of this have moved closer to the CMB constraints from Planck, but the uncertainties have shrunk so much that the tension has actually increased. So, and especially you can see this with these points here on the left. This is the isotropic BO measurements, where you can see that a lot of these points at lower redshifts are lower than the CMB prediction, and this is what drives that tension that Christian was telling you about yesterday. So in the final few minutes, I want to tell you about our attempts to go beyond BAO, so to extract more cosmological information. And here I'll focus on what I've been doing for the last year and a half on the side while also doing the BAO analysis. So this is the laminar alpha forest full shape analysis. And here we have two types of measurements that we're using. So we have this very high redshift quasars. When I say high redshift, I mean 2 to 4. I know there are people here for whom that's not high redshift. So what we do here is first we measure the laminar alpha autocorrelation function, and this means we're correlating the absorbed flux from neutral hydrogen in the spectra of this high redshift quasars, but we're also measuring the cross correlation between that absorbed flux and the quasar positions. And you can see the BO peak in both of these correlation functions, and in this case, what we're aiming for is to actually extract cosmology from the shape of those correlations, so going beyond that BO peak. And there's two primary effects that we're after. The first one is the Alko-Paczynski effect. So this is an anisotropy that's introduced into our measurements because of an assumption of the fiducial cosmology. So when I was showing you how we build that histogram, what was hidden in there is that when you do that histogram, you need the distances, the co-moving distances between each galaxy pair. But what you're measuring is redshifts and angles on the sky. So you need to assume some fiducial cosmology to translate those redshifts and angles into co-moving distances. And obviously, we want to measure the true cosmology, so we probably are not going to get it right. And the difference or the ratio between our fiducial cosmology or the distance in our fiducial cosmology and the true cosmology will give you this Alko-Paczynski effect. The second one is redshift space distortions. I won't have time to go into this in today's talk. Here we're trying to measure this growth of structure or F sigma 8 parameter, but if you're curious, please come talk to me afterwards. So this is just another view in the anisotropy. This is a compression of the same correlations that I was showing you before, but now as a function of the line of sight angle theta. So on the left, you have pairs that are along the line of sight, aligned along the line of sight, and then on the right, pairs that are across the line of sight. And the fact that this line is not flat means that we have some anisotropy. And then this Alko-Paczynski effect is actually controlling something like the curvature of this anisotropy. And that makes it quite different from all of the systematics and redshift space distortion, so we are able to tell it apart. And when you propagate our measurement from DESI DR1 to cosmological constraints, you see something like the picture here when you assume flat lambda CDM. So the blue measurement is our Lyman alpha full shape constraint. Most of this is from Alko-Paczynski plus BAO. And you can see how it aligns with the Planck CMB constraints in orange and the galaxy BO measurements in black. So you can see that this tension between DESI and the CMB is between the galaxies at lower redshift and the CMB. And then the Lyman alpha angle right now is right along this tension, and we're not powerful yet to be able to see whether our results would agree more with the CMB or with the galaxy clustering, but we expect this to improve significantly in the next few years. And of course, all of these measurements are lower when we're talking about the Hubble constant with respect to shoes, but they all assume flat lambda CDM. When it comes to dark energy constraints, the Lyman alpha constraints, when you're combining them with the CMB and supernovae, they help tighten the constraints, and actually it cuts off this high tail away from lambda CDM. But because it cuts off this tail away from lambda CDM, it doesn't actually significantly increase the tension. Now, interestingly, when you combine them with CMB and with a combination of the cosmic microwave background and galaxy BAO, it doesn't significantly affect the uncertainty, but it shifts the whole contour, which you can see here in pink, closer to the lambda CDM constraint. And to give you a better idea of how these measurements help constrain dark energy and what we're thinking about and hoping to see in the next few years, in my final slide, I want to build you this picture of what our measurements are actually contributing to the dark energy constraints. So here I'm showing the BO measurements from DESI-DR2. At the top, it's the isotropic measurements. At the bottom, it's the Alko-Paczynski measurements. And then here in blue, this is the constraint when you assume the W0 WA CDM, so evolving dark energy. Whereas the black line, that's the CMB, the lambda CDM prediction from the CMB. So essentially, if you're trying to figure out whether the universe is better described by lambda CDM or by an evolving dark energy equation of state, you should try to have new BAO or Alko-Paczynski measurements that help you tell these two lines apart. So in terms of BAO, that means improving your BO constraints at these low redshifts, because this is where the two lines are apart. If you have new BO constraints at high redshift, that's not actually going to help, because this is very tightly constrained by the CMB. And then on the Alko-Paczynski side, what we're looking for is this high redshift measurement, so above redshift 1. But you can see that the difference between these two lines, it's about 2%, whereas our measurements are in that area as well. And actually, if I add now the DR1 full shape results that I was just telling you about, you can see that we're getting a little bit better with the results from DR1. And actually that red point there, which is combining the Alko-Paczynski from the DR1 full shape analysis with the Lyman alpha BO result from DR2, that's a 1.3% constraint. And here are the forecasts that we currently have for what we're going to be able to do with these measurements with 8 years of DESI. And then we're also in the process of planning this DESI-2 survey, which is going to deliver another set of really tight constraints from the Lyman alpha forest. So if you're interested in this, please come talk to me afterwards. And thank you very much for listening. And I'll leave you with this beautiful fly-through through our DESI-DR2 data.
Thanks so much, Andre. Time for a couple questions. Yep.
Andre, very nice talk. I really enjoyed it. A bit of a whimsical question, so you can take it with a grain of salt. But since BAO measurements, BAO was discovered 20 years ago, they've always been considered very robust, I think. But since the tensions have emerged between DESI BAO and lambda CDM and Planck, I've heard some people question the reliability of BAO measurements. I guess my question for you is, has your confidence been in BAO measurements been affected by the appearance of tensions?
That's an interesting question. I guess whenever you get a really surprising result, as a good scientist, I think you need to go back and rethink, have I actually checked everything that's important? Of course, because we're doing this blinding process, and it's really nerve-wracking when you get to the unblinding moment, you've already done that. But yes, when you see something surprising, it sort of makes you go and rethink if we checked everything. And actually now in DR2, we took that approach very seriously, and we thought about, okay, if we're seeing the surprising results that indicate that dark energy might be evolving, what are all of the things in our analysis that could lead to that due to some systematic reasons? And we didn't find anything in DR2 that could potentially explain that. And actually, in order to explain this tension with just systematics in BAO, it would be incredibly difficult. And the reason behind that is that the BAO measurement is just very robust, because all you care about is measuring that the position of that BAO peak that allows you to marginalize over unknown unknowns that affect the full shape or the broadband of your correlation function. So there's very few things that actually can give you a systematic shift in the BAO measurements, and also do that across the different redshift bins that we have in our analysis. but yes, again, every new, and even now for when we're working on DR3, we're again thinking from the perspective of, if we get this wrong in some way, can this impact our dark energy results, or is there anything that could do that?
So what did you think of George Evstathiou's paper about the DESI DR2?
Maybe this is a good chat. I believe. We can maybe have a quick question while Stephen comes and gets set up.
Stephen has a question.
Stephen can ask the question while he walks down here to get set up, perhaps.
Are you worried about the role of nonlinearities in your output efficiency measurement?
The role of what? Sorry.
Nonlinearity.
Yes. So that's always the fight that we're fighting. So in this analysis, I didn't went into too much detail, but we're largely sticking to large linear scales. And one of the significant parts of this analysis is whether we have any indication that we are sensitive to nonlinearity. So we have these empirical models from hydro simulations that are have been shown to fit the Lyman alpha power spectrum to very high K, and we're always fitting and leaving all of those parameters to be free. And what we're looking for is actually, are we actually sensitive to them, right? We don't trust necessarily those models that if we can fit those nonlinearities that will deliver robust cosmology. What we're looking at this stage is, are our cuts keeping us at large linear scales where we know we can trust our analysis?
All right, let's thank Andre again.
And next we have Stephen.
Wait, how do we have to do this?
However you want to. I guess clip that onto your shirt and move it into the pocket.
Oh, okay.
Okay. Excellent. So Stephen's going to tell us about peculiar velocities. Exciting stuff.
Yeah.
Good to hear.
Sure. Yeah. So hi everyone. I'm Stephen. This is my first year here, so I want to thank everybody. Thank the organizers, and it's great to see all of you. I want to talk about kind of a curious, maybe slightly esoteric thing. So I've been working in this area of the effective field theory of large-scale structure to predict things like what Andre was just talking about and what Kristen was talking about, the cluster of galaxies in Lyman alpha for a number of years. And I was just recently thinking about, is there a way we can take this to weigh in on other kinds of statistics of galaxies? And so today I'm going to talk about this kind of curious connection that what we've been doing for DESI and other surveys like this has to do with them. So how do we measure peculiar velocities? Just a quick recap for people who are not so familiar. So typically in galaxy surveys, we measure the distances of galaxies by their redshifts, right? So what we do is we take a spectrum of a galaxy, and you say, okay, I know that this is supposed to have some wavelength, and I measure it at a slightly different wavelength. And from that, I can measure, the scale factor of the universe from which it was measured, and that gives me a line of sight distance. However, this distance we measure, of course, is degenerate with the Doppler. Did I say the Doppler effect? The Doppler effect, or there's a different guy that discovered it. Nobody credits him. So it turns out that this thing is degenerate with the Doppler effect. So what you really measure when you measure the redshift, or 1 plus the redshift z, is 1 plus z times the cosmological redshift times 1 plus z from the peculiar velocities. And for non-relativistic velocity, that roughly goes as the velocity over c. However, if I can now measure the distance to the galaxies independently of that, then I can pull out the effect of, how does this work? Then I can pull out the separate factor, right? So how can I do that? Well, we have many ways to measure distances of galaxies. One way is to do it via for example, the fundamental plane or Tully-Fisher for just galaxies, right? So here, I believe for the fundamental plane, I get the size of the galaxy. For Tully-Fisher, no, it's one of those. Anyways, I can either get the size or the magnitude of those galaxies, again, for the distance, or if I have a standard candle like supernovae, then I can also use them to figure out the cosmological distance directly. And in fact, for cosmological measurements of supernovae, what you typically do, in fact, is say that these peculiar velocities incur some kind of scatter in your measured Hubble diagram, and you input that into the error bars of your analysis. So really, trying to figure out, trying to disentangle this term is in some ways trying to take this kind of noise of these distance measurements and turning that into a signal. So, and why should I want to do that, right? So why should we measure peculiar velocities? Why do or should, right? Well, the interesting thing is that the peculiar velocities trace the exact same large-scale structure as galaxies. So here I'm showing the nonlinear density field Here's taken from this picture by Marcel Schmitzel. And you can see that the velocity field, if you stare closely enough, these are almost the same field in Fourier space except multiplied by some factor. So what you do is you measure, a different manifestation of the primordial density of galaxies, of the initial conditions, but you directly measure the growth of structure because galaxies are biased tracers of the density field, but velocities, because of the equivalence principle, every single velocity is, for every galaxy, because we're all subject to the exact same gravitational potential, you directly trace its growth of structure. And moreover, what you can see in this picture is that, the galaxy field has a lot of detail on small scales, but the velocity field is actually coherent on very large scales. So the signal, where the signal to noise between these two kinds of fields is very different. Here I get a lot of exquisite small scale clustering, and here I can really trace very large cosmological scales. So how are we going to approach this problem? So I work in this formalism called the effective field theory of large-scale structure. And what that roughly means is that you take this kind of very simple insight, which is on a very large scale, the formation of structure in the universe looks a lot like a weakly coupled gravitational fluid. So we know on small scales, this is not all what happened. On small scales, we have this really complicated system where at the very least we have collision with dark matter that has a complicated phase-space structure. But as I zoom out more and more, so if I take this picture and I zoom, if I smooth and smooth and smooth, eventually I end up with a system that really looks like just a fluid that obeys the continuity and Euler equations, but with dynamics sourced by the gravitational potential. So the effective field theory of large-scale structure is just a way to make this formal, right? To answer the question, why can I study structure formation at all when what happens on small astrophysical scales is very, very complicated, right? Why don't I have to worry about how the explosions of supernovae impact the large-scale, the large-scale dynamics of galaxies? And what you get out is basically that the universe looks like this fluid, except with a term that is kind of an effective stress tensor, very much like the sound speed and the various kind of shear terms when you look at, say, water, right? In water we have the exact same picture. Water is very, very complicated. It's a lot of molecules on small scale, but when I zoom out, all I'm left with is some effective stress tensor. And by doing this, I can really predict the clustering of galaxies with smaller and smaller scales in a consistent way. Whereas if I did not include these kind of effective corrections, I would get, even as I go higher and higher order in the perturbation theory, the theory will simply not converge, right? You see here, for example, the next leading order correction does even worse than linear theory if I don't include the effective theory corrections. And why is this important? Well, the important thing is that the large scale part, right, this part of the equation that I haven't highlighted in blue, is not free. All these things depend just on one cosmological factor, which is the expansion history of the universe, the Hubble constant here. So if I study large-scale clustering while marginalizing over these effective terms, then I can really study things like the large-scale growth of structure that constrains things like general relativity or deviations from it, or late-time dark energy evolution. So here I'm showing, for example, this plot of future peculiar velocity measurements just from galaxy clustering alone, plus peculiar velocities, and you can see, for example, for various modified gravity theories, you can really distinguish them just by measuring this kind of structure formation. And this is especially interesting because these peculiar velocity surveys I was talking about will then be able to probe these dynamics at very, very late times, which is exactly when, if we have, for example, evolving dark energy, the impact on structure formation will be at its greatest. And so just to answer a question many people have, what exactly are we expanding and how is this theory defined? And so roughly you can think of, you can think of this theory as being valid when the overdensity of the universe is small, right? So very roughly, we define some scale where the overdensity of the universe is of order 1, and once you pass order 1, once you get to scales of, say, 0.2 per inverse megaparsec, the theory breaks down, right? And so we're really working with a theory that works from the scale of the cosmological horizon all the way to this nonlinear scale, and past this, who knows what happens. And so this allows it to hit scales about k of 0.2 at redshift 0, where these peculiar velocity surveys will. So does it work? In the past many years, some colleagues, many people, including myself, have been working on using this to predict galaxy clustering. And you can see, I particularly like this plot that we made a few years ago, where you can see that the predictions of the theory compared to fully nonlinear n-body simulations is really, these two things are really able to agree at really the sub-percent level. So taking this, in the past few years, we've really been able to apply these to galaxy surveys like DESI to measure the 2 or 3 point function and so on. And for example, my student Mark Maus last year, was able to leverage all this and use our code velocileptors. I'll explain that. Please don't ask me what velocileptors means. But we were able to use this to show that we're really able to extract cosmological parameters from say, like galaxy clustering in DESI well beyond the statistical requirements of really any realistic survey. So then the question is, can we extend this to peculiar velocities? And I'm sensing that I'm probably running a little time. And the answer is yes. So the answer is, again, because for most galaxy surveys, we infer the distance directly from the redshift. And this already means that we have to understand the role of peculiar velocities compared to galaxies. Oh dear. OK, yes. I think I'm running out of time. So I'll speed through this. And so what this really means is that I'm already using the fact that galaxies are moving along, are being displaced apparently from the inferred distances by their peculiar velocities. And so what this really means, to show the one equation I will in this talk, is that the observed density of galaxies is equal to their true positions with a Dirac delta function that relates their observed position plus to their real position plus their velocity, right? So what this actually means is that it turns out that all of the statistics of peculiar velocities, all the clustering of galaxies can be described by the pairwise motions of galaxies. And so I'm showing here two things we might want to measure. For example, if I have two galaxies separated by some distance, I might want to ask how much on average are they falling towards each other. And so you can see here, for example, if I have a galaxy centered here, of course, on large scales, they will tend to fall towards the galaxies. Or I can ask the question, what's the relative velocity dispersion of this infall? And again, you get this thing where when they get very close, the interhalo motions mean that, that there's a huge scatter on very small scales and relatively even stuff on large scales. And so what this means, I'm skipping past a bit. If I had more time, I'd describe it. What this means is that actually the clustering of galaxies in redshift space that we measure for surveys like DESI is directly related to these peculiar velocity statistics just by a simple derivative. So each derivative gives me a new peculiar velocity. And that means that the models that we have used already for DESI to do full-shape galaxy clustering uniquely specify every single peculiar velocity statistic you can measure. And what this means is if I take the mocks of galaxies that I use in the DESI survey, for example, and measure their peculiar velocities, this one model is able to predict all these things with no free parameters, which actually is very powerful, because if I now have a survey like DESI, which will measure both of these things, I can use these new statistics to break all the parameter degeneracies and actually measure the EFT parameters directly. And what you can see is that it actually works quite well. Well, it works about as well as the predicted scale of K of about 0.2. And just one final thing that I'll mention is that this relation between these things has a very interesting consequence for the BAO. So one thing, so Andre and Christian talk about how we can do this, how we can measure BAO, and one of the main complications of measuring the BAO is that structure formation actually smooths out the BAO, right? So here in this picture, you can see if the BAO starts out in this perfect ring, the random motions of galaxies will tend to smear it out. And what you get, roughly, is that the BAO's feature of galaxies is damped roughly by something that looks like an exponential damping. And this exponential damping, part of it comes from the fact that there are lots of random velocities that move things along the line of sight like this. And so we use this formula that relates the clustering of galaxies to the peculiar velocities. What you see is that when you take a derivative of this formula, the BAO and the peculiar velocities no longer looks like just a pure damping, but rather has some weird polynomial dependence. And so what this predicts actually is that the BAO feature in peculiar velocities, unlike that of galaxies, actually changes sign and phase very quickly, even on very, very large scales. And what you can see in this plot actually is exactly this. So this dashed line here is what you would expect for galaxies or for linear theory. But when you measure the BAO feature in peculiar velocities, you can see that even at very large scales, they immediately change sign relative to the leading order prediction. And this is something that is actually a very explicit confirmation that our theory for the BAO in galaxies is correct, right? Because this is a direct prediction, again, from our models for galaxy clustering, which shows really, there was a question earlier, how can we know that BAO is robust? I think this is really a super sub% prediction that we can do this from a completely independent probe. And so the question, okay, finally let me end with, can we actually use these models to measure structure formation? Can we use these to constrain dark energy? And as a simple test, I asked the question, can we measure the growth rate of structure? And it turns out when you test these theories on simulations, we can recover the growth rate of structure, which directly probes, say, dark energy at better than 0.4% from this combination of galaxy clustering and their velocities, which is 5 times better in the same volume compared to just galaxy clustering alone. And this 0.4%, I want to emphasize, this bound is not limited by the theory. This bound is really even for the full volume of Desi Mach. This is this is as good as we can get on the growth rate. So the theory really works at least as good as the full statistical power of these Machs that we're using for Desi. So in summary, the particular velocities are predicted by the exact same EFT prediction for galaxies in retrospace, so we can leverage these old theory developments for new things. And I think with the coming years, we'll get more of these measurements from things like LSST and from Desi, and which will really allow us to grow structure formation in the late universe.
Questions? I'll kick us off. So this sounds like a really cool way to kind of model the peculiar velocities. Is it possible to use this to kind of make the peculiar velocity corrections to some data that people use more precise, or is that kind of not needed?
Yeah, I think that's very much one of the next things one can do. So you can see in this. Well, you can see this plot here is that the peculiar velocities are really a very important part as you go to very low redshifts. And so one thing which I didn't mention is that there's been a lot of developments on doing kind of field level modeling of structure formation, and so doing that with this kind of EFT approach can really allow you to reconstruct the bulk flows in the local universe in kind of a model independent way. And so I think that's one fairly promising way to do things. In fact, the people who currently do peculiar velocity surveys already do something very much like this, but they really only stop at linear theory. So they kind of really have to extrapolate a lot. You have to assume a lot about this to make it work. And so this is kind of just in some ways the next step.
Very cool. Very cool. Final questions before coffee? I think we all probably need some caffeine. So let's end it there. And thanks, Stephen, one more time. Don't run away. We have to get a photo first. Okay. Group photo. Follow Andy, I guess.
Out front.
That way, out front. Okay. And then coffee. And when are we back?